Welcome to the 46th lecture in our series. So last time I had started discussing multilinear maps on vector spaces, and I had introduced the operation of tensor product of two multilinear maps. Now using the tensor product operation, I want to get a nice basis for this. I start with some finite dimensional vector spaces V1 up to Vk, and I look at multilinear maps of V1 cross the Cartesian product of these Vi's, which we have denoted by this L of V1, V2, Vk all the way up to and to the target being R. Now the building blocks for this basis will be these one forms. In other words, a basis of one forms, namely the dual basis of dual basis. So of course when I say dual basis, what I'm already assuming that I start with a basis for Vi, then get a dual basis for Vi star. So let's I'd stopped at this point. The claim is then, as we have seen before, if I take the tensor product of all these one forms, I get an element of LV1, V2, Vk. So the claim is that all those tensor products will give me a basis. So I look at the collection of all omega I1 for each of this. So this I1 is just keeping track of which vector space I am at, and then within that there is a whole bunch of possibilities. So let me use J1 to denote that tensor omega Ik and then Jk. This can be a bit confusing, but it becomes clear if we explicitly mention the range of these indices. For instance, this I1 here, all the I1 up to Ik, this set is essentially keeping track of this is just a 1 all the way up to k. It's just a permutation of this 1 up to k. So nothing much going on here. As for this, now there's more freedom in this superscript, and this J1 for instance will vary from 1 to N1. No, sorry, the vector space here is I1. So N I1 Jk will vary from N Ik. So perhaps as an example, let's just deal with the simplest case. I have two vector spaces, k equals just 2, let's say. So I start with a basis V with our notation V1 1 V1 N1. So this is a basis for V1, and then V2 1 V2 N2 basis for V2, and then we get a dual basis which is the index comes below omega 1 N1. Oops. 1 and 1 basis for V1 star omega 2 1 omega 2 and 2 basis for V2 star. And then what we are now what we are claiming is that one wants a basis for L V1 V2 R. So what I claim is that look at all the collection of all tensor products of every element in this first set here with every element in the second set. So in other words, one look at omega, so just to be consistent, so I have used I and J. So so let's use the same notation. I1 J1 tensor omega I2 J2. So this and I1 comma I2, these is just a permutation of 1 comma 2. Actually, right, so here one has to be, in the case of different vector spaces, one has to be slightly more careful. Notice that when I have two different vector spaces, I have to be a bit more cautious here. So when I have two different vector spaces, and if I have so with my notation, omega 1 is an element of V1 star, omega 2 is an element of V2 star, then omega 1 tensor omega 2 is an element of L V1 V2 R. But right, omega, so this makes perfect sense the way I have defined it. However, if I look at omega 2 tensor omega 1, this is not quite an element of LV1 comma V2 R. So the reason being, of course, that the way we defined it, omega 1 tensor omega 2 is going to be a mapping from V1 cross V2. So the first variable necessarily is from V1. While if I write it like this, the first variable will have to be from V2. So this is not inside this, in this space. This one is. Now if V1 equals V2, then both of these will be inside this. It doesn't, both of them are well defined and both of them belong to that. So here, for instance, when I write I1 up to ik, so it's not, I have to be actually, I can't even permute them in general. So let me just erase this. So I'll necessarily have to deal with this stuff. So J1, the rest remains the same. So when k equals 2, so this is a basis for this and this is a basis for this. So here too I have to make a small change. So this is I just have, in fact it's simpler. So omega 1, omega 2, and then I no longer have to mention this. So J1 is going to vary from 1 to N1. J2 is going to vary from 1 to N2. The collection of all these tensor products is a basis. This is the claim basis for L V1 comma V2 R. And notice that if we count how many elements there are, well, J1 can vary from 1 to N1 and J2 can vary from 1 to N2. So there are exactly N1 N2 elements here. And that is going to be in the general setup also, that's going to be the case. So let me mention in particular dimension of V1 VKR is N1, the product of all the dimensions of the underlying vector spaces. So let's prove this. The proof is simple enough. So proof. So we want to show that these elements these multilinear forms, multilinear maps actually form a span this L V1 V2 Vk, and they are linearly independent. So let's just check that they span. So in other words, any multilinear map can be expressed as a linear combination of these special one multilinear maps. So let's check that. So let's give it a name, actually this set, the what we want to be the basis. So let B, let's call this, so set B spans L V1 VKR. That is the first thing. And i.e. given F in L VKR, we can find F now J1 up to Jk, F J1 dot 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 Jk in R such that of course as usual it's not a single number, so these Ji's vary from 1 to Ni. So we can find all these numbers such that F can be written as a linear combination F J1 and Jk, and then this basis elements which I had here, omega I1 to the power omega I1 J1 etc. Omega I1 J1 tensor omega K Jk. So this is the claim that we can find. So in fact so we have to come up with these constants F J1 Jk for all possible values of J1 Jk, and it's clear how to find these coefficients. The idea is very simple. You just evaluate F on basis vectors, then these special forms, multilinear maps, will all be 0 except the ones with the right index. So in fact let's take let F J1 Jk be equal to F of Vj1. Oh, I have to be again careful with whether I use a superscript when I go between one forms and vectors. The superscript changes. So for this it is, yeah, okay, V I1, right, V1, J1, Vk, Jk. So these are the some basis vectors that we started with. So I evaluate the given multilinear map on certain basis vectors and I get a number. I call that as fj1jk, and this j1jk keeps track of which basis vector I am plugging in here. The same index which is occurring here will be here. So let's take these coefficients. With the claim is that with the choice of these coefficients, then this equation then star holds. Well, when we say star holds, remember that both sides are multilinear maps. So we have an equation of two multilinear maps. In other words, if I plug in any k, if I evaluate the multilinear map on any k vectors, I should get the same thing. So let's see that we do get the same thing. So let V1 all the way up to Vk, the domain of this map F is V1 belong to V1 times Vk. Then here on the right side I have a linear combination of multilinear maps. So let's evaluate each term separately. In particular, let's just evaluate, and this is just this f is just a constant here. I evaluate this tensor product, then omega I1 J1 tensor omega Ik Jk acting on V1 Vk equals this entire thing acting on this equals, so well, by definition of tensor product, this is omega 1 J1 V1 dot dot omega k Jk Vk. Now we can simplify this further. So Vi, after all, each of these vectors, these are arbitrary vectors in this vector spaces. So V1 itself, and I already have basis for all of these vector spaces. So let's write V1 as in terms of the basis vectors. Perhaps it's better, instead of if V has already been used, let's use X. Let X1, and that will also make it clear that these are variables. So X1, Xk, omega 1 X1, Xk. And so let's express these xi in terms of, we can write x1 equals summation x1 I1 V. So I1 equals is an index running from 1 to n1. Similarly, all the way up to xk. Xk equals Ik running from 1 to nk. X, I put a k here, Ik, Vik, and then k here. Once I do that, then omega 1, so now I want to look at this, omega 1 J1 X1 will be I1 equal to 1 to N1 x1 I1 omega 1 j1 acting on v I1 1. Now, by the very definition of a dual basis, the only way, if j1 is not equal to I1, I get this term here is equal to 0 if j1 not equal to I1 equal to 1 if j1 equal to I1. So, when it is 1, so the only term which will survive is I1 equals j1, and when I1 equals j1 I just get this coefficient. So, this is x1 j1, right. So, and the same thing happens for all of them. So, finally, this thing here can be written as x1 j1 xk jk, and therefore remember that we were in the process of evaluating, so we wanted to check that this equation holds. So, we evaluated both sides on this k tuple of vectors x1 up to xk. On the left hand side I get, so this is not, therefore LHS of the equation star is f of x1 up to xk. RHS of star is, that's what all these simplifications show. RHS of star is summation of this summation of f j1 jk, f j1 all the way up to jk, and then x1 j1 xk jk. So, we have to show that this LHS this equal to this, but we haven't used the definition of f j1 jk. This is f evaluated on, this is the definition. So, what we have here is the definition of f j1 jk, v1 j1 vk jk, v1 j1 vk jk, this times f j1 xk jk. So, we have to show that this quantity here is the same as this, and that follows immediately from multilinearity. So, by multilinearity of f. In other words, I just write, so for example, the first step in proving this would be, I just, instead of x1 I use the, I won't complete the whole calculation, let me just indicate how it goes. F x1 all the way up to xk, instead of x1 I plug in the expansion of x1 in terms of the basis as I have defined it here, x I1 v1 I1. And the other stuff I keep as they are. Then I get a summation over I1 and then x this I1 and then f of v I1 1 x2 xk. In the next step, so this is a summation if over the index I1. For each I1 I can instead of x2 I can plug in the expansion of x2 and again expand. So finally I'll get a sum which involves only these terms that I have here, and these coefficients come out as expected. So I'll just write etc. So that completes the statement that these special multilinear maps obtained by tensor product of one forms actually span the full space of multilinear forms. Now let's prove that this B is linearly independent. Again, the same calculation can be used. So here, suppose some linear combination is 0. Suppose some linear combination. Now, the linear combination, where was I? Right. So this, the right hand side. Let's again say here we don't have a multilinear map, but I'll just use the symbol capital F for the coefficients. I need some coefficients. I'll use this capital F and omega I1 J1, omega 1 J1 tensor product, all this omega K Jk equal to 0. So the fact that this is 0 means that it's a 0 as a multilinear map. Evaluating this at, so I just take a basis all the inputs are basis vectors, just like I did here. So I1 V1 I1 VK VK IK. When I evaluate this, the same calculation as earlier shows that this thing here evaluated on this will be 0 unless these indices I1, I2, Ik coincide with J1, J2, Jk. We see that, and when they coincide I just get 1. So the only term which will survive in this big sum is when the index J1, J2, Jk is I1, I2, Ik. So that will give me this constant here, F I1 Ik equal to 0. And this is true for all such I1 up to Ik. So therefore all coefficients are 0. So one sees that they are linearly independent as well. So just to be clear, what we have used is Fj1 omega k jk evaluated on V1 I1 comma Vik k equals 0 if this J1 Jk is not equal to I1 Ik. So even if one index here is different, the whole product will be 0. Otherwise it is 1. If J1 Jk equal to I1 Ik. That's immediate from the definition of the tensor product. After all, this number here is, we have already done that calculation, but let me just write it. Omega 1 J1 thing on V1 I1 omega k jk evaluated on Vik Vik, and here it's a k. So this thing here is exactly equal to this, and here the moment one of these indices ji is not equal to, well, jp is not equal to ip, then this thing will be 0. The corresponding term will be 0. So we get the required thing. So this is a good point to stop here. And in the next class, we'll talk about special kinds of multilinear maps and then move on to differential forms. Okay, thank you.